And just although everyone can hear it now, all speakers, I'll just give you a name, and then as I asked you, please present yourself as part of the introduction. So I'm not using time on saying who you are and what you're talking about. So. So just to confirm, Avi, you are not. You're not saying anything before I take over. Is that true?
Yeah, you can just take over on the hour and start the session.
Perfect. Thanks a lot. So good day, good morning, good afternoon, good night, wherever you are. We are now ready to start the second day on the TESS Science Conference. My name is Hans Kjeldsen. I'm from the Stellar Astrophysics Center at Aarhus University, and I'm a member of the SOC for the conference. We have a first session in this session 3 with 5 talks. I should remind you that there's a Slack channel for questions. You can, of course, write questions there throughout the talk or when we start the question session. So I will read those questions you ask to the individual speakers. And if there are more questions than time allow you, these can of course be answered later also by the speaker. So just to make sure the Slack channel, and we use asteroseismology for the first part, although one of the talks are probably not much about asteroseismology. And then for the next session, I will come back to that. But first speaker, an invited overview talk is Michael Pedersen. Please, Mike, and I will stop sharing here. So please, Mike, take it over.
Okay. Again, good morning, everyone. My name is Michael Pedersen, and I'm a postdoc at the KITP at UC Santa Barbara. And so I'd like to thank the organizers for inviting me to come here and give this overview talk about asteroseismology with TESS. But first of all, it's a starting point. If we have a look at stellar evolution, then we tend to see stars as evolving in 2 different ways, depending on their initial mass. Now, however, when we try to study stellar evolution, one of the issues that we have is that while the lives of these stars are mainly governed by what's taking place inside of the stars, what we observe is their surface properties. So about 100 years ago, one of the questions that was raised was what kind of appliance can we use to pierce through the outer layers of stars and study and test the conditions inside of them. And so for that, asteroseismology has taken inspiration from seismology, the study of earthquakes. And in asteroseismology, we are studying the oscillation of stars that penetrate deep into the interiors of stars and thereby carry information about the conditions inside of them. And so the goal of us, astroseismologists, what we really want to try to do for you is to provide you with a good set of fundamental stellar parameters derived from astroseismology, as well as provide constraints about the interior properties of the stars, such as the mixing, angular momentum transport, and magnetic fields, and so forth, will have a major impact on the evolution of the stars. Now, if we look at oscillations, stars tend to oscillate in 2 kinds of oscillation modes. One is the pressure modes, which have pressure as the restoring force, and the other is the gravity modes, where gravity acts as the restoring force. And as you'll see in these propagation diagrams, the pressure modes mainly have the highest probing power in the envelopes of the stars, whereas the gravity modes have the highest probing power near the cores of the stars themselves. So that means we can use these different types of oscillations to learn about different parts of the stars themselves. Now, when we study oscillations of stars, we try to assign them a set of quantum numbers to characterize the oscillations. And these quantum numbers tells you something about the number of nodes that the oscillations have. So one of the quantum numbers, L, the degree L, tells you about the number of nodes on the surface of the stars, which is where the oscillations are not moving. The azimuthal order M tells you the number of nodes that are crossing the equator, whereas the radial order N tells you the number of nodes that the oscillation has inside of the star. And in order to do astroseismic modeling, we need to have this mode identification for the oscillations. Now, there are different ways we can go about to try to get these mode identifications, also depending on whether we have pressure modes or gravity modes. So one way is we can utilize the pressure modes, roughly equally spaced in frequency. So if we chop up our frequency spectrum in equal segments of frequency, what we end up seeing is these kind of ridges in these HGL diagrams, as we call it. For gravity modes, what we're utilizing is that these modes are roughly equally spaced in periods. So the modes with the same number of the same L and M value form these kind of period spacing patterns, which we can then use to derive the mode identification of the oscillations. And finally, if we have a rotating star, a slightly rotating star, what you end up seeing is that your oscillation frequencies get split. And this number of splitting depends on the degree L of the mode. And in that way, we can use this to assign mode identification to the stars themselves. Now, we do have ways to learn about some properties of the stars without having this mode identification, such as the stars like the solar-like stars, which oscillate in pressure modes and have this characteristic kind of comb-like feature in the power spectrum. And so what's the case for these stars is that the large frequency separation between modes of the same degree L and the frequency of maximum power can be used in combination with the effective temperatures to estimate the mass and radius of the stars, and thereby tell us about this information about the stars themselves. Now, for the remainder of this talk, I'm going to take you on a tour through the asteroseismic HR diagram, which might be a bit more of a sprint. So hold on tight, I'll say. So a lot of this work has been carried out by the TESS Asteroseismic Science Consortium. There's a lot of work being carried out about these different types of oscillators, and I cannot at all cover all of it, so I apologize in advance. But the important part I want you to take away from this special HR diagram is that it tells you if at any point during the evolution your star falls inside one of these regions, that it should start to pulsate. And that if it's pulsating, that means we can learn something about the interiors and parameters of these stars. Now, starting at the low mass end, we're going to show you a bit of results from solar-like oscillators and red giants. So the diagram we have here on the right is actually from Kepler data. But what I'm using here is to try to show you what happens to this comb-like feature in the power spectrum as the stars evolve. So as the star evolves, the comb-like feature moves towards the left in this diagram, and the oscillation amplitudes also become larger. So that means in general, it's much easier for us to study these type of oscillations in red giants. So also for this, I will mainly be focusing on red giants for this talk. So one recent result, focusing on the study of red giants in the southern continuous viewing zone observed by TESS. And the detection and determination of these, the nu max, the frequency of maximum power, and delta nu, this large frequency separation. And so out of this entire sample that was included in this study, both of these parameters were derived for 41% of the stars in this sample, of the stars in this continuous viewing zone. And for a subset of these stars, the study also provides the masses and ages of the stars. And one important part I want to point out here that they highlight in this study as well is if you have a luminosity estimate from Gaia, then that's actually going to help you with your uncertainties on the ages and masses that you get for these stars as well. Another recent result that's come out is an archive. I don't think it's published yet, but it's there. Is a comparison of the Kepler field and red giants observed there. So the Kepler field of view was reobserved by TESS in sector 14 and 15. And so what this study focused on is trying to estimate how well TESS does at actually detecting these comb-like features in the power spectrum. And so with this control sample from Kepler, what they find is that in about half of the cases, they're able to recover and able to detect this nu max value, whereas it's much more difficult for these stars to detect this large frequency separation, and it becomes increasingly easier to do so the higher number of sectors that we have. If we also compare it to the uncertainties that we get on these parameters, so we have the large frequency separation from TESS compared to the ones derived from Kepler data, and the nu max from TESS and Kepler. then with the uncertainties that we get, that translates uncertainties on the radii, masses, and ages as the ones that you get here on the right. Now, as I showed you here, TESS is not going to is not finding as easy to detect these red giants. What's great about TESS is that it's observing a lot of stars. So Mark-Han will talk a bit more about this later during the conference, but I just want to highlight that TESS can really do a lot of contribution for these red giants because of this large sky survey that it's doing. So look forward to the talk by Mark later. Now for the next part of the diagram, we're going to move a bit higher up in the HR diagram and look at these main sequence in 8 A and F type stars. And as you can see in this very, very small part of the diagram, we have a lot of different types of stars that are pulsating. So that's super interesting. It means there's a lot of interesting physics we can learn for these stars, a lot of stuff to be done. And so for some initial results that was carried out by one of the working groups of TESS was to carry out a variability study for some of these A and F type stars observed by TESS. So one of these initial studies are shown here on the left, where the stars have been put in the HR diagram and compared the position to the predicted instability strips. So this black line, full line, is the predicted instability strip of Delta Scuti stars that oscillate in pressure modes. And the black dashed line is the instability strip from the Gamma Dorado stars, which oscillate in gravity modes. So for another sample of these stars called the Lambda Boo stars, which are at least thought to be metal poor, a recent study has also been made to study the oscillations in these stars and look at the fraction of these stars that oscillate as Delta Scuti type oscillators. And as what's actually found for these stars is that these stars have a higher fraction of oscillating stars compared to the normal, so to speak, A-type stars that we have in this sample, which is another interesting result from looking at this TESS data. Another thing I want to point out is that now with TESS, a sample of TESS stars, it's been possible to estimate and get a mode identification for some of the Delta Scuti stars. So an issue with Delta Scuti stars is that you don't have all modes excited of these oscillations, contrary to what we see from solar-like stars. And also because of rotation of the stars, this makes it a lot more difficult to get the proper mode identification of the oscillations. But what's recently been shown is that at least for a subset of these Delta Scuti stars, you can use the same mechanism, the same method of these shell diagrams to actually estimate to get mode identification for some of these Delta Scuti stars. So that means now we can actually start carrying out asteroseismic modeling for a larger sample of these stars than what has been done before. Another set of interesting stars in this very narrow part of the HR diagram is the rapidly oscillating AP stars. So those are magnetic stars that have large global magnetic fields, and these global magnetic fields give rise to these abundant spots that then give rise to rotational modulation of the light curve, as we observe. So these stars are also found to have very rapid oscillations, and it's also been shown that their pulsation axis is offset from the rotation axis and is somewhere in between the rotation axis and the magnetic field axis for these stars. And so it is shown here in an example of such a rapid oscillating AP star, where on the top you see clearly the signal from the rotation modulation. And if we remove the signal from this, we end up recovering these oscillations of the stars. So pre-TESS, there's not that many of these stars known, but just from I think the first cycle, as far as I remember, of observations from TESS, we actually have 20 new such detections of these stars. So TESS is really contributing a lot for these type of oscillators. Now the last new discovery for these type of stars I wanted to mention before moving on to the rest of the HR diagram is the discovery of these kind of single-sided pulsators. So these are stars in binary systems where you see on top really the orbital signal from the variation due to binarity in the light curve. And on the bottom panel, you see what the oscillation signature looks like for this star once that the orbital signal has been removed. And what you see here is that at certain phases of this orbit, the amplitude of the oscillations become much larger than at the other phases. So that means that the one side of this star is actually oscillating at a higher amplitude than the other one. So TESS is the first time we've detected such a star. They've been theorized to exist before. And in this case, what has happened here is actually that we have an oscillating star where the pulsation axis is in the direction of the lineup axis between these two binary stars. And TESS hasn't only found one star, there's also a second one available. So this is a second such detection of a single-sided pulsator from TESS data. Now, moving up in this diagram, briefly, if we move in the right direction, we get to the higher mass stars in the HR diagram, which are found to oscillate in pressure modes and gravity modes, depending on which type of star that we have. What's also been found is that these stars tend to show stochastic low frequency variability, which is seen as this power excess at low frequencies. And I'm going to leave that to Dominic. He's speaking right after me to go into a lot more detail about this. And Matteo Cangiello is also going to be talking about these signatures later on during the conference. But what I really want to emphasize for these stars is that TESS is really contributing to the studies of these higher mass stars, especially compared to Kepler, where because of the choice of the Kepler field of view, we actually didn't have any of the high mass stars observed by the nominal Kepler mission. So now with TESS, we've managed to do some initial variability studies for the stars observed by TESS at this upper main sequence. And I also encourage you to go and have a look at the poster by Simon Bursens, who had done asteroseismic modeling for one of the stars in this diagram as well. Now, an additional thing I wanted to mention, and I'm not going to go into much detail, but what's also been recently found for red giants and yellow supergiants, that these stars also show stochastic low frequency variability, and a new type of oscillators has also recently been discovered. And Trevor Dorn-Wallenstein is going to be talking more about this, so I'm not going to cover more about this part of the HR diagram, but just move on to the last part, talking about a set of compact pulsators and some of the studies and results that have been obtained with TESS. So for these compact pulsators, you'll see that the oscillations have low periods. And some of the initial studies that we have is if we start looking at the hot subdwarf, then we have from the initial TESS observations, a new detection of such a subdwarf by TESS oscillating in gravity modes. And for this particular subdwarf, oscillating gravity modes, it was possible to obtain the lowest mass estimate for one of these stars yet. And also for the first time through the asteroseismic modeling of these oscillations, it was also possible to infer the core oxygen and mass fraction for these stars at this stage of evolution. Another interesting thing that's been found is for some of these hot subdwarfs, it appears that the dipole modes that we see in the stars are located at higher frequencies than what we would normally expect to see. So usually for these stars, we have two examples up here. One was included, this one was studied by TESS, where the oscillations are much higher frequencies where you would normally expect to see the L=2 modes for these stars. Now, the last asteroseismic result I'm going to mention is from a study of white dwarfs or pre-white dwarfs. So these are from, I guess, the highest luminosity white dwarfs in our HR diagram, where for this subset of stars called GW-Vir stars, these are stars that are on the cusp of becoming white dwarfs. And what was possible here was to use the TESS data combined with extra data from ground-based observations as well to get period spacing patterns for the stars and use these in asteroseismic modeling to not only derive the mass of the stars, but also determine whether the stars had already entered the white dwarf cooling sequence or hadn't entered just yet, so to speak. So that's a new result. So looking forward, TESS has lots of promising stuff coming with the new section of observations coming up. So what I was very excited to hear is also how the cadence of the full frame images is going to be reduced in the future. And so what that means is if we, for example, look at the solar-like oscillators and these cone-like features, so in the 30 minutes cadence, full frame images at 10, 4, and 2, you see a clear difference between which stars we can actually study these solar-like oscillations. So basically what this is telling you is that for the 4-minute cadence, we can actually observe these features in younger stars just from the full frame images alone. If you look at the rapidly oscillating AP stars, the 4-minute cadence is also going to make it possible to study these oscillations in some of the stars. And I think I counted about half of the stars in Daniel Holdsworth's paper. Whereas for some of the stars, we still need for sure these 2-minute cadence data to be able to study these oscillations in the stars. And finally, I wanted to briefly mention, and maybe Dominic will cover that as well, but also these shorter cadences means that we will be able to more easily detect these stochastic low frequency signatures of the stars. So with that, I want to finish saying that TESS is really a treasure trove for pulsating stars across the HR diagram. It's providing this large unbiased full sky survey of stars, meaning that stars that were not accessible as easily before has now become so. It's allowing for a lot of major new opportunities for discoveries, and also allowing us to study larger samples of stars of a certain type of oscillator. And I think I'll end with that. And thank you very much for joining and attending this first session of the Astroseismology session.
Thanks a lot, Mai. You cannot hear the rest, but okay, so we go to the questions, and just remind all of you that you can ask questions in the Slack channel, use hashtag Astroseismology, and we already have a few, and even if we don't manage to answer all of them, she can of course go in and write the answers later. So I will start with the first question from Brett Skinner. How might the study of these oscillations be affected by emission type and rapidly rotating type stars? In other words, how do these types of stars affect their oscillations?
Right. So for one, so let's say rapidly rotating example. So let's say, for example, the BE stars is one example of rapidly rotating stars that also showing emission line of H alpha. So for these stars, what you're actually seeing is outbursts in the light curves for these stars. And this has also been detected by TESS. I couldn't cover it here. But what is actually seen, as far as I remember, is when you have these outbursts, some of the amplitudes of the oscillations, they increase in a sense, and you also start getting additional frequency groups. Generally, rapid rotation tends to shift your frequencies into different frequency regimes. So in some cases, for sure, it makes it a lot more difficult to do mode identification for the stars. That's one issue, but it's also really, really interesting to study for these stars. I'm happy to address more in Slack.
Then there's another one from David Ciardi. Thank you for a really nice overview of some amazing results by the community. for the binary stars, which make up roughly half of stellar systems, which with single-sided pulsations. What are the expectations for the effect on stellar evolution? And has this been accounted for in the modeling? Thank you again.
For the single-sided pulsations and stellar evolution, it has not been accounted for. So this is this is really, really new discoveries, and I don't recall seeing anything where this has been taken into account. Someone else knows more, they're also welcome to address in the Slack, but this is really a new finding. So it's been predicted before that we'd expect to see that pulsation axes get aligned with the line of axis, say from tidal interactions, but this is the first time it's actually been observed. So that it's really new. I'm not gonna, even try to predict what's gonna happen for the evolution for these stars. But yeah, it's true. Binary stars is a big group that I have not really addressed at all, and there's a lot more to be learned for these stars as well.
Okay, we will have to move on to the next speaker, but first, George Ricker actually pointed out that the cadence in the upcoming extended mission is planned to be 200 seconds, not 4 minutes. So it's even better than what you about, Mai. So I thought we should just remember this.
Yes,
the seismic
that's
community.
amazing. For the full frame images.
Yes, for full frame images, 200 seconds. So
great.
Thank you, George, for also making sure that that can happen. Well, thanks again, Mai, for this presentation, and please go to the Slack channel later, and you can, of course, all of you ask more questions there. Then the second talk or presentation of this first session is by Dominic. So please, Dominic, the floor is yours. So.
Thank you very much, Hans, and thank you to the organizers for allowing me to speak today. Hopefully you are seeing slides, and if not, please shout at me. But I'm going to talk to you today about how TESS has really opened up, as Maya has just talked about, the massive star asteroseismology potential, and in particular the gravity waves, this type of pulsations that we now detect almost ubiquitously in massive stars, is connected to their mysterious macroturbulent broadening. I've not mentioned, I'm Dominic, postdoc at KU Leuven in Belgium, and I'm a research fellow of the FWO. So that means I get to work on whatever I want, and that means 99% of the time I'm working on fantastic TESS data. So Maya's already showed you this diagram on the left, and this is the asteroseismic HR diagram, and the green box denotes the parameter space that I'm going to talk about today. So stars that have spectral types of O or B, main sequence and immediately post-main sequence, which TESS has really shown us have this seemingly ubiquitous detection of stochastic low-frequency variability. So this SLF variability that you'll see in the literature. On the bottom of the slide on the right here, I'm showing you just an example of a light curve of what one of these stars looks like. And you see there is both long period and short period variability. And on the right-hand side is the amplitude spectrum, the periodogram of this variability. And there are two important features that I want to point out that seem to be very common in massive stars. And it's only really with the high quality TESS data that we're able to exploit this for the first time. And the first of these features is this background of stochastic variability. And the second is that a lot of these massive stars have coherent oscillation modes. So there are two different types of variability going on here. There's the peaks, the coherent oscillations that sit on top of this ensemble stochastic background. And what we really want to do is exploit both of these, because as I'll show you in the later part of my talks, they're doing different things, and we can really use them to extract parameters of the stars. So this is just an example of the known pulsating massive stars from cycle 1. So this is only cycle 1 because there's too much data for just me to look at, so I can't keep up. So that's a good thing. But here is the upper parameter space of the main sequence. And this is a review paper that I published last year on massive star asteroseismology. So if you're interested, please go have a look at that. But you can see that there is a lot of pulsating stars that sort of correspond to where we expect them to be, but there's also stars that are located where we don't expect them to pulsate, and vice versa. So TESS has allowed us to probe the excitation of pulsations in massive stars as well. So a couple of years ago in Boston, when we could all be in the room together, I showed you a plot that looks like this. And this was the first deep dive into what TESS gave us for massive stars. And we used both K2, TESS, and Gaia information to map out how this stochastic variability changes as a function of the stellar parameters. And in particular, if you fit the stochastic low frequency variability with this semi-Lorentzian function, you can characterize it with an amplitude, a characteristic frequency, a steepness parameter. And what we find is that the brighter, so the more massive, the more luminous stars have higher amplitudes and lower frequencies on average. And that this morphology that we see in the amplitude spectrum is also insensitive to the metallicity. And this is a sample that includes both subsolar massive stars in the LMC and supersolar stars in the galaxy. So this is telling us that whatever the mechanism is, doesn't seem to be very sensitive on the intrinsic metallicity of the star, and there's a common morphology across all of the stars. What I really want to talk to you about today, and this is the subject of my talk, is how we can go further. So in those 2 years, I haven't just been on holiday. We've been looking at combining TESS photometry with high resolution spectroscopy. And specifically, I want to highlight the Jakob database for massive OB type stars, which is all high resolution, high signal to noise spectroscopy. And this is led by Sergio Simon Diaz, who's the PI of Jakob. So we've been able to cross-match the TESS database with the 2-minute cadence light curves, which we need a high cadence to study the stochastic low frequency variability. And we've matched this with the Jakob database, and we've put them in the spectroscopic HR diagram. So if on the left, I could draw your attention to the location of the stars in this diagram. And if you pay attention to the high mass stars, so everything above maybe 20 solar masses, you can see that there's a clear trend as you go from the 0-age main sequence towards the terminal age main sequence. The dots get a bit more dark in color, so they go from yellow to purple. And this is color coded by the amplitude of that stochastic variability. So as stars age, the amplitude of their variability increases. And if you draw your attention to the right-hand side now, the same diagram with the same sample of stars, but now color-coded by the characteristic turnover frequency. And you can see that there's a sort of quasi-monotonic relationship here where it goes from purple to yellow in the opposite. So now what this is telling us is that the frequencies decrease as the stars age. And so this stochastic low-frequency variability is directly probing stellar evolution. So in the future, we hope to extract the masses and the radii, the ages and the luminosity just from the TESS light curve, because it is probing those parameters. And so whatever mechanism this is, it really has to probe the stellar structure. And so this is an exciting prospect to get fundamental parameters directly from the TESS light curve. Now, onto the mechanism itself. So there are a few different ones. So the first that I want to talk about is the gravity waves that are excited by core convection. And the second that I'll leave to Matteo, because he's going to talk about this on Friday, is that we've got variability caused from the subsurface convection zone. So on the right here, again, I'm showing you an example of another TESS light curve of a massive star and the amplitude spectrum on the bottom panel here. And the reason why I would like to convince you today that core convection is at least in part, if not the dominant mechanism of explaining of this stochastic low frequency variability, is that we find that the observed ensemble spectrum consists of a large range of frequencies. And also the frequency range is very, very broad. So you've got variability from days all the way up to minutes. And if we go one step further and we compare this to full 3D hydro simulations that we have available for massive stars, we find a remarkable similarity between the extracted wave spectrum near the surface of the star and what we see in TESS observations. And so what we can do is a direct comparison with the hydro simulations, and we find that the dominant variability at the surface seems to be these large scale L equals 1, 2, 3, for example, waves that are excited from the core convection. And just play that movie one more time. You can see the the dipole action of the core convection, and I'm showing you part of the envelope here with those beautiful waves dancing up and down. So core convection is a big mechanism to consider, in my opinion, because it is a very large convective engine that we find during the whole of the main sequence. And this large convective engine is able to excite those large degree waves that we see at the surface. Now, how is this related to macroturbulence? Well, there are a couple of different broadening mechanisms. So changing gears to spectroscopy now that we find for massive stars. The first is, of course, rotation, which I'm not going to talk about because that's one of the most fundamental broadening mechanisms in spectroscopy. But the two that become increasingly more important as you go up the main sequence are microturbulence and macroturbulence. And microturbulence is commonly referred to small scale, and it's been linked to the subsurface convection zone. So again, Matteo's papers very nicely illustrate the physics that we expect to happen as a function of, for example, luminosity and mass on the main sequence here. And on the other side, the large scale broadening mechanism is referred to as macroturbulence. And from an observational point of view, these are essentially fudge factors. These are terms that we include in the analysis of spectroscopy to understand the shape of spectral lines. But there is underlying physics to explain why these broadening mechanisms exist. And the goal here is to try and understand what the physics is to cause those mechanisms. And so macroturbulence is commonly referred to large scale, and it's predominantly a horizontal motion in the line forming region near the surface. And this has been historically linked to pulsations because these gravity waves have predominantly horizontal motion. So there seems to be a link from the spectroscopic research in the last few decades that suggests that the increasing detection of pulsations as you go up the main sequence, and now this TESS photometry is really adding to this evidence that as you go up the main sequence, you see larger amplitude pulsations in both photometry and spectroscopy, and this is related to the macroturbulent broadening and the line profile variability that we commonly see in massive stars. And I'd also like to just highlight the difference in scale here when I talk about the broadening in terms of kilometers per second. Micro can be anything from a few up to maybe 10 or 15 kilometers per second, which is expected to increase as the star reaches the terminal age main sequence. And macroturbulence, I'm showing you the average here of a large sample of O-type stars. And there are exceptions, for example, magnetic stars, which are believed to have very, very low macroturbulence. But sometimes macroturbulent broadening can be in the hundreds of kilometers per second. So there's a difference in scale between these two values here. So how is this related to gravity waves? Well, using the 3D hydro simulations of stellar interiors, you can directly extract the velocity field that you get from gravity waves excited by core convection. And so this is something that Ertz and Rogers did in 2015, and they showed that based on simulations of line profile variability, that gravity waves have a good match to the observed line profile variability at the surface. So on the left here, each gray line here is a spectral line, and you can see the line is moving around because of the pulsations. And on the right, this is a series of observations, and so you see there's a very good match here between them. So this is spectroscopically, macroturbulence obviously been very strongly linked to pulsations. And we can go one step further now by adding the TESS photometry. As I mentioned, the predominantly horizontal motion that gravity waves provide, we also find a very strong correlation between the amplitude of the stochastic low frequency variability on the x-axis here and the magnitude of the macroturbulence that we find. So this is, again, complementary but supporting evidence that whatever the mechanism of macroturbulence is, it seems to be very strongly linked to pulsations, and the simulations of core convection are able to provide the necessary predominantly horizontal velocity field that we need near the surface to explain observations. So with that, I've got 30 seconds left, and so I'll give you my takeaway messages. I have to show this beautiful figure on the right here from Sergio and Abel. I haven't talked about the post-main sequence. I'll leave that to other people. But of course, all of the things that we're learning about the main sequence propagate into the post-main sequence, and TESS is really opening up the Hertzsprung gap for astroseismic studies as well. But what I've hopefully convinced you about today is that massive stars show both coherent modes and stochastic variability, which is caused by gravity waves. And this is nearly ubiquitous in the massive stars, and we can use it to probe the masses and the ages, at least indirectly, directly from the TESS light curves. And we've linked that now to macroturbulence, which is the large-scale, predominantly tangential velocity field, which we believe is caused by gravity waves from core convection. Finally, I'll just refer you to Simon Bersens, who's my PhD student. He has a beautiful poster on how we've exploited TESS data to do asteroseismic modeling of the first OB-type stars in the continuous viewing zone in the north. And with that, I'd thank you for your attention and happy to take any questions.
Thank you, Dominic. Okay, we have time for at least one question, and I just take the one that was asked by Steve Carla on the Slack channel. The low degree modes driving by core convection are ones that would be most visible in disk integrated photometry and spectroscopy. Can we say anything about the higher degree modes that would be less visible, or are they spatially patterns decoupled from the driving geometry?
That's a really good question. Thanks, Steve. So we've actually been thinking about this for a while now, because a lot of the geometric cancellation arguments are made based on periodic, so perfectly coherent oscillations. So when you have one part of the limb moving towards you, you have another part of the limb moving away from you, and so these high degree modes tend to cancel out. But with stochastic oscillations, this is not really the case, because you've got different parts of the limb that are not perfectly in antiphase with one another. So what we're seeing, what we think we're seeing, is actually a much broader range of angular degrees than we normally would see based on coherent oscillations. So I'm not going to put a definite number on it, because it depends on the star, the rotation, the inclination, etc. But what we do seem to find is that the predominant signal is from L equals 1, 2, 3, 4, and maybe a few others. The core convection is again a nice explanation of this, because you need a very large driving region to be able to, I mean, an L equals 1 wave is a very large, has a very large propagation region. So you need a big engine to drive those. So I think the jury's still out on exactly the angular degree range, but this is something that we're looking into.
Thanks a lot, Dominic. There are more questions on the Slack. I ask you to go there, Dominic, and answer those. So, but thanks again for this brilliant talk.
Thank you very much, everyone. Enjoy the rest of the conference.
Thanks. So the next one is Simon Murphy. Simon, please go ahead.
Thank you, Hans. Today, I am talking about a young star that's chemically peculiar due to its planet-forming disk, and I'll start off just by explaining how we know those things. So this star, whose name is HD 139614, lies in Upper Centaurus Lupus, which is part of SCO-CEN. And what I have here is an age map of SCO-CEN. So what you're seeing in blue is the youngest stars at about 5 megayears. And then in the dark red are the older stars, which are still objectively quite young at an age of about 28 megayears. And one thing you'll notice from this map is that there is a clear age gradient across the sky here. In the upper left of the diagram, we've got the younger stars, the blue coloring. And then as we move towards the lower right, there's a fairly smooth transition to older stars. But there is also what we call age dispersion. There's a lot of clumpiness here. For instance, there's a region down here where the stars are older than you would expect based simply on an age gradient. And what this means is that it can be quite difficult to infer precise ages of stars simply from maps like this. So for HD 139614, we infer an age of about 14 plus or minus 3 megayears. Whereas with asteroseismology, that is by modeling the stellar pulsations, we get an age of about 10.75 megayears with a smaller uncertainty. And that tells us that this star is on the pre-main sequence. This star is also chemically peculiar. It belongs to the Lambda Boo class. And these stars have underabundances of refractory elements. So those are elements that readily incorporate into dust grains. So those are typically the iron peak elements. And for this star, you can see underabundances of about half a dex. Whereas they have volatile elements in roughly solar abundance. So carbon, nitrogen, oxygen have roughly solar abundance. So from spectroscopy, we would infer a metal mass fraction of about 0.004. Whereas from the asteroseismic modeling, we get a higher metal mass fraction of 0.01. And then the star has this planet-forming disk. The disk is warped, it has ring structures, and it has cavities. So on this image on the left, you can see that close into the star on the left-hand side, the disk is illuminated, whereas as you move farther away, the disk is not illuminated, and that's indicative of the disk being warped. The next image here shows the various ring structures that have been identified in scattered light photometry. And then on the far right here, we have a model of the integrated optical depth, which shows a gap in the disk, which is attributed to embedded protoplanets. Now, this star has been studied with asteroseismology, and thanks to Pedersen's brilliant introduction, I don't have to spend much time on this slide. There's just a couple of points I'd like to emphasize, and that's that if you observe modes of different degrees and different radial orders, those will penetrate to different depths within the star. Now, we might expect a star to be centrally condensed, so its density is higher in the center, and the pulsation modes in their various degrees and radial orders are sensitive to those changes in density. And so we can infer the interior composition and the age of the star if we can identify pulsation modes and we can measure their frequencies precisely. So for this, we turn to TESS. The top panel here is the TESS light curve at 2-minute cadence for this star. It's a delta Scuti star, so it's pulsating. It has a mass of about 1.7 solar masses. And the bottom panel is the Fourier transform of that TESS light curve. Now, I don't want you to focus too much on the circles and the triangles at the moment. What I want to point out here is that this star has a fairly regular pattern of pulsation modes, and that's quite unusual for delta Scuti stars. So I've drawn here dashed vertical lines at multiples of the large spacing at 6.83 cycles per day. And you should notice that the peaks that are identified with little triangles occur just to the right of the dashed lines each time, so they're regularly spaced. Now this value, delta nu, the asteroseismic large spacing, goes as the square root of the mean stellar density. So if we observe a large delta nu, the star is denser. As I say, this is a new quantity for delta Scuti stars, and we know that 6.83 cycles per day is quite large for a delta Scuti star based on a sample of 60 stars in a paper led by Tim Bedding last year. And so this star is very dense and hence very young, very close to the zero-age main sequence. Now, when we analyze these pulsations, we use a tool called the Echelle diagram that Mai described a little bit. I'll just talk you through that in a little bit more detail. We take the Fourier transform and we divide it up into equal segments of size delta nu. Then we stack those segments vertically. We encode the amplitude information with color, and that forms the Echelle diagram. I'll just go through that one more time. We take the Fourier transform and we divide it into equal segments of size delta nu, and then we stack those segments vertically. We encode that amplitude information with color, and that forms the Echelle diagram. Here's the Echelle diagram for this star. The Fourier transform that I showed previously had triangles and circles on it, and those same triangles and circles are shown in the Echelle diagram on the right-hand side. And what we notice is a very clear ridge down the left-hand side of the diagram and a curved ridge down the center. Thanks to the paper last year that Tim Bedding led, we know that the modes in the left-hand ridge are L=1 modes, and the modes in the ridge down the center are L=0 modes. Those are the radial modes. Now, mode identification was previously intractable for this type of star, for delta Scuti stars. We just never had this many modes identified before. For this star, we identify 7 dipole modes and 4 radial modes, and that gives us the chance to probe the age and the composition of the star. So we did some modeling. Our goal here was chi-squared minimization. So in the open symbols, those are our model frequencies, and the filled red symbols are our observed frequencies that you saw in the previous slide. You have to be really careful with your mode identification. The strongest peak in each row is not necessarily the peak that belongs to the pattern. So you might naively expect that the lowest degree modes, the L=1 and 0 modes, would be the strongest and they would be in the pattern, but that's not the case. So what we did is we constructed 10 mode ID scenarios where we accounted for the fact that the strongest peaks might not be in the pattern. And that allowed us to make sure that at least one of our scenarios was going to have the correct mode ID and would get the lowest chi-squared. So we constructed a grid using MESA and Jaya, and our starting point here, I'm showing this in an HR diagram in the top left, was this little green box, and that's the classical error box in temperature and luminosity. We used a roughly solar metallicity as our starting point, and we put a prior on age that the star should be less than 30 mega years old, and we know that based on the stellar association. And then the large panel on the right shows all of our models, and this is in the mass and metallicity plane. So each point here is one of the models calculated by Meredith Joyce. But actually each point's not representing only one model, because each point in this grid is evaluated at many different age steps, and also with different parameters for the mixing length alpha. And what's shown is the point in the stack that has the lowest chi-squared. And you see that there's a global chi-squared minimum reached here, and we've sampled a wide parameter space surrounding it to make sure that we have found the global minimum and not just a local minimum. So what you can do is make a corner plot out of all of these models. Here, the gray circles represent all of the 10 to the 5 models that we evaluated. And in color, we have our best fitting models, plural. So these are the models with chi-squared less than 1. In red, we've got a convex hull, which encapsulates all of the points that are consistent with the observed temperature and luminosity. So the colored points inside the red polygons are where our best fitting models lie. And in this, we were able to achieve a 1% precision on mass, 10% precision on the metallicity, 7% precision on age. And we also found no dependence on the mixing length. And that's kind of to be expected. This is a very young star. It's recently been fully convective. It's very homogeneous. And so the strength of mixing doesn't really influence the stellar structure too much at this point. So how is it that we get such precise values? Well, on the left here is the same HR diagram that I showed previously. And these are 6 tracks with slightly different masses of the same metallicity. And then in the panel on the right, what I'm showing is the delta nu, that's the large frequency separation, as a function of age. And you can see that delta nu changes very rapidly for these stars, and there is mass sensitivity. And that's partly because the evolution on the pre-main sequence being such a rapid phase is very sensitive to the stellar mass. But also you have to think that the density of the star is changing very quickly as it condenses towards the 0-age main sequence. And that means that the pulsation frequencies are changing very rapidly too. So in summary, HD 139614 is a young star. It's still in the pre-main sequence. We get an asteroseismic age of 10.7 mega years. It's also chemically peculiar. While the spectroscopy, which really only probes the photosphere, shows a metal mass fraction around 0.004, the asteroseismic metal mass fraction is significantly higher, and that really samples the bulk composition of the star, showing that the star is chemically peculiar. And the star has this planet-forming disk. It's a warped disk, it has ring structures, it has cavities, and this is suggestive of embedded protoplanets. And one of the selling points of this talk was that I was going to say how these planets cause this chemical peculiarity. So if you'll allow me one more slide, I'll talk you through that. So the planets trap dust, but not gas. So the planets are trapping these refractory elements that, like the iron peak elements, that readily incorporate into dust grains. And this changes the composition of material that then accretes onto the star. So while the Astroseismology showed the bulk composition is almost solar, the surface abundance is affected by this selective accretion. This is observational confirmation of a theory developed by Michael Kama some years ago now. And there is more work on this star disconnection to come, particularly using these brilliant TESS data and using the Delta Scuti pulsations. Thank you very much.
A second. Thank you, Simon. And you are well in time, so we have time for a few questions. The first one by Travis Midcalf. How large are the systematic age uncertainties likely to be for the massive stars?
That's a really good question. So this star, I forget the exact mass, somewhere between 1.5 and 1.7 solar masses. So not anywhere near as massive as the stars that Dominic was talking about. Yeah, the systematic age uncertainties can come from a few different places. One of the things is what you consider to be the start of the stellar evolution. And if you look at various stellar evolution codes and the way that they treat the start of the evolution, or basically what they call age equals 0, the difference is really on the order of something like 10 to the 5 years at most. And this star is 10 to the 7 years old, and our uncertainty that we quote is 10 to the 6 years, more or less. So that's not a major source of systematic uncertainty. And then there are various other things that you could consider, such as the opacities that you use or the nuclear network that you use, whether stellar rotation is changing the stellar structure very much. All of these can contribute to your uncertainties. And I think we discussed all three of those in the paper. And basically individually, they're considerably smaller than our quoted uncertainties. So our uncertainties do to some extent take into account some of these systematic uncertainties.
Okay, we have time for more questions. I just go to David Ciardi. That last result is really interesting about the planets. So are you saying that the Lambertoti stars should all have planets? And is there a prediction for the minimum mass planets needed?
Yeah, really good question. There are actually, I believe that there are a few different mechanisms that can cause the Landabou peculiarity. And when I say believe, it's because there are a few viable mechanisms proposed, and they, given the current observations, not all of them can be ruled in or out. And one of the mechanisms is the one that I'm presenting here. Another one would be sort of perturbed exocomets in a debris disk, and that could happen sort of any time in the stellar evolution, really, sort of through maybe dynamical interactions with planets. What we see if we look at the age distribution of Landabou stars is that you have quite a few near the zero age main sequence. So these are young stars, presumably their peculiarities come from interactions with a planet-forming disk like I'm showing here. And then there are also quite a few near the terminal age main sequence, but it's not truly bimodal. There is a fairly smooth range. I hope that answers your question.
Okay, final, and if you can answer quick by Vicky and Tochi. Great talk. What about rotation? Young stars are often very rapidly rotated.
Yep, very good point. This star has a measured V sin I. The V sin I is 24 kilometers per second, which is actually very slow for a star of this spectral type. But we also know that the star is seen at a fairly low inclination because we have observations of the disk. So we know the inclination, I believe, my recollection, something like 18 degrees. And we came up with an equatorial rotation velocity of something like 70 to 80 kilometers per second, which is still slow for a star like this. There's an ongoing modeling effort to treat rotation properly and also to try and model accretion. That's our next work to do with this star. So stay tuned. Okay, thanks, Simon, again. And then the next speaker is Krzysztof Hełminiak. Chris, please, the stage is yours. So.
Thank you. Thank you for the invitation, for the opportunity to present my work. I'm going to talk mostly about eclipsing binaries and my spectroscopic survey supported by TESS photometry. There's a lot of people also contributing to it, to this large project, including some of the attendees here, Fred Markadon, Ayush Moharana, and Tilak Pawar. I will first, because it's the first talk about eclipsing binaries, is one of the very few on the conference, so I will just give a short introduction to the TESS eclipsing binaries. Then to the CREME project, our guest investigator programs on TESS, and some results and conclusions. So the TESS eclipsing binaries are one of the most interesting and most useful objects in astronomy, stellar astrophysics, especially if they are also spectroscopic binaries, double-line spectroscopic binaries. We get a lot of crucial key parameters for the stars from those objects. parameters that are difficult or impossible to get another way. The many options to use the results are, I mean, the list is long, so starting from testing the stellar structure and evolution to studying discrepancies, testing formation scenarios, then finding some new rare cases, improving calibrations, then going to the distance distance ladders, space to cosmology even, and to general relativity. The list of the applications is very long. That's why for many years, for several decades now, there was an interest in getting precise parameters for those objects. Currently, the best compilation is the catalog called DepCat, maintained by John Southworth. Currently, it contains 269 binaries with very precise parameters. And by very precise, I mean better than 2% uncertainty. And with some information about temperatures, but not all the information are available for all the systems. For example, a large fraction of them do not have estimates of metallicity or abundances. And as you can see on this figure, this is a mass radius diagram. For this sample, the primaries are with orange, the secondaries in the systems are shown with green dots. There are places where we have plenty of cases, but then there are very underpopulated regions, like the larger mass side, the low mass end of the main sequence, the low mass pre-main sequence phase, then the giants and subgiants, and then of course there's a Hertzsprung gap somewhere here. So there's a lot of space to improve the situation, and that was more or less the goal of the CREME project. CREME stands for Comprehensive Research with Echells on the Most Interesting Eclipsing Binaries. So the goal was to identify some new examples of those rare and poorly studied interesting detached eclipsing binaries and characterize them as precisely as we can and get as many information as we can. On the same mass radius diagram, I'm showing you some of the cases for which we have the masses and radii calculated. As you can see, we go inside the Hertzsprung gap, we go to the giants, we go to massive stars, we go a little bit lower in the, we go a little bit in the low mass end of the main sequence. There are also other characteristics not seen in this diagram that are interesting for us, like multiplicity, pulsations, etc., and a lot of other things, activity, chemical peculiarity. So the idea was to have high quality spectroscopic data for a large number of objects selected blindly from, almost blindly from a photometric survey. It all started around over a decade ago on the southern hemisphere. Then as the project evolved, we also moved to the north, and then the observational part, the spectroscopic observational part, is almost done, except for some cases where we had additional time this year. And then, as you can, well, you can see some of the telescopes that were used for this project. But in fact, in total, we used 16 telescopes and 18 spectrographs of those telescopes. Currently, the project observed something like 380 targets. Out of those, so far, 160 were classified as interesting for one or other reason. We have now something around 5,000 high-resolution spectra. By high resolution, I mean higher than 20,000. Usually it's around 30, 40, 50,000. This is the list of the spectrographs that were mostly used. There are 4 major instruments. So the HIDES in Okayama in Japan, Chiron in CTIO, Coralie, my personal favorite telescope in the Swiss telescope in La Silla, and the Pharos on the NPG telescope also in La Silla. Bunch of other spectrographs used for the observations, and single spectra that are coming from other facilities and also from archives if they are available. Currently, we are at something like 23, 25 papers, either directly related to the project or using the data from the project. Then there are other groups that use our spectra that are in the archives, like in the ESO archive. The whole project contributed to 1 habilitation, 3 PhD degrees. There are 2 more PhDs coming on, 1 Bachelor of Science, and there were some also press notes. So to get the parameters that we want precisely, we also needed precise photometry, which was a problem at the beginning because we had access to the public surveys like ACES or SuperWASP, and it turned out it not to be good enough for our purposes. So we wanted to have our own photometry, and getting 300 targets, dedicated photometry, ground-based for 300 targets is a problem. But suddenly there was TESS, and most of our problems were fixed immediately. So we started applying for the GI, guest investigator programs. We got all the cycles. During all the cycles, we got some data. Last time I checked, after sector 40, we had already 240 targets observed with 2-minute cadence, most of them in 1 sector, but sometimes up to 13 or 15 sectors. 2 of those targets are in the continuous viewing zones. So TESS has been really the key source of our photometric data. Question is, somebody may ask why 2 minutes instead of 30 minutes? Well, the answer came from Kepler, and one of the targets we observed and used the Kepler photometry. The blue curve here is the bottom of the eclipse, the minimum. The blue dots are from the 30-minute data. The red dots are from 2-minute data. This part here, you can see the end of the eclipse, the egress. So you can see there is a difference. Of course, this is due to the smearing effect. But once you model a system like that, and you finish the modeling of the light curve, and you plot the residuals, this is what you get for the 30-minute data, and this is what you get for 2-minute data. If you want to see how it affects the results, the stellar parameters, this is mass radius diagram for the 2 components of this system, where you cannot fit a single age for those for the 2 components in case of 30-minute photometry. But when you move to 2-minute photometry and the model made on this 2-minute data, everything fits perfectly. So this is our justification for applying for the GI and 2-minute cadence. So with TESS data and creme spectroscopy, we so far produced something like 25 models of 20-something eclipsing systems. So far, there are 5 publications printed. There are other publications submitted or in preparation, and some conference proceedings as well. We are also aware of a paper produced by another group on the target that was proposed to GI by us, which is great. I mean, we all contribute to the field. So the results, some examples of some results. This system, AI Phoenici, should be familiar to anybody who is working on eclipsing binaries. This is one of the best studied and most popular stars in the field. So of course, several groups proposed 2-minute photometry on TESS, including ourselves. And Pierre Max, that was the one that organized a group of people who are working on eclipsing binaries and asked them to make models with their own codes, with their own approaches, in order to check the realistic uncertainties and errors in stellar radii in this case. So the conclusion is that all those in those graphs, each dot, each color is a different approach, different model. So the conclusion is that it is possible to reach the level of uncertainty like 0.2% in the radius. Because this is CREME as a spectroscopic survey aimed also for mass. We also monitored the AI Phoenici system for a very, very long time, currently also around over a decade. And so far, with the data that we have right now and the model that still does not include all the effects that can be seen in this system, we are reaching 0.08 error in M sin I. So this tells us that this star tells us that both mass and radius can be calculated down to really sub-percent precision. 0.1% is something that should be accessible right now. From another results, pre-main sequence stars are one of those among those groups that we are interested in. There is a multiple system called V1200 Centauri, which we found earlier and studied earlier, but then with TESS we also asked for the 2-minute photometry and got some new spectroscopy, and we revisited the system, mainly to confirm if it's a pre-main sequence. And we found that the secondary is actually with this mass, 0.86 solar mass, it has over 1.15 solar radii, which is too large for the main sequence. And in this way, we confirmed that it's probably a PMS. We also found it's a hierarchical multiple, most likely a quadruple system with the inner binary period 2.5 days and 180 days of the outer orbit. And the interesting part is that probably due to the influence of the third light and third and fourth components, the components of the inner binary are not coeval. If you want to see the details, please check the poster 8.06 by Fred Marcadon or check his paper, which is also available. Then my personal favorite topic is Loma stars.
Chris, you're running out of time, so maybe go to sorry for that. Quickly about Loma stars. Those when we reapplied the test data to our previous results, we also of course found that we have better precision in stellar parameters, like in these two cases. These are the models with the test data, so not much into detail here. This is also a new case where we can see a Lomas binary. I want to draw your attention to this plot, which is the out of eclipse variation, that shows spots that evolve very quickly in time. This is not the fastest evolving spot in the case, but that we've seen, but one of those that made a lot of problems for us. The results on giants and subgiants, I just briefly mentioned that we also have some. Then there are tight triples, a new contribution to the project with the so defined as the eclipsing binaries with the third star on a orbit shorter than 1,000 days. One of the recent examples is shown here, but you can also see it on the poster by Ayush Moharana. Please see poster 619 for all the details. Another factor that also connects to the astroseismology are the pulsating stars in detached eclipsing binaries.
We focused on that because we found some cases in Kepler field that were not found by the pulsation search algorithms, but we found them to be pulsators after we analyzed after we got the mass and radius and saw that, okay, they are in the delta Scuti, somewhere in the gamma Doradus, instability zone, and turned out they both have gamma Doradus components. So we are now running a program on finding more of such stars. Some of the examples are shown here with the TESS data. This is a very strange case. But this one, AI Hydra, is actually a delta Scuti pulsator known for already known, but has been revisited by Tilak Pavar, and you can go to his poster 917 to see his results. So conclusions. Of course, when you get a lot of observations on a lot of objects, you get you get a lot of interesting ones. That's obvious. But some of the characteristics show up only with spectroscopy. So combination of precise photometry and spectroscopy is crucial, especially if we want to get the parameters very well measured, like in these cases that I showed. The activity can be a problem, or spots, or other things that show up on the surface of the star. But still, 0.5 or 1% error is possible. And few words about the future prospects. Okay, so last slide. I was happy to see that the cycle 4 covered a little bit of the ecliptic plane, where we found more of our systems, and then we're building a large database of several hundred systems with a very precise determination of parameters that can be used for other studies. Thank you very much.
Thanks a lot, Chris. There is a question on Slack. Please go and answer that there. We have
okay. Thank you
for a question, but thanks a lot, Chris. The final talk of this first session 3 by Sam Grunblatt. So please, Sam, take the scene.
All right, can everyone see my screen?
Yes.
Okay, great. So thanks for the introduction, Hans. And so I'm a postdoctoral fellow at the American Museum of Natural History and the Center for Computational Astrophysics. And today I'll be talking about age dating red giant stars using observations from TESS with implications for galactic archaeology. And as I know many of us at this conference are more familiar with other subfields of astrophysics, I figured I'd start off this talk in the same place that I first started this project, which is on Google. So if you Google galactic archaeology, the first definition that pops up is this one, where you're highlighting that galactic archaeology is essentially the study of tracing the history and formation of our Milky Way. And so I just wanted to point out that in 2 of the 4 images that occupy the top of Google image search, you see that one of the key features are these streams of stars that extend beyond the plane of the galaxy, and they're essentially like perpendicular or not at all related to the plane of the galaxy, implying that these streams that are essential to galactic archaeology have positions and motions that are very different from the other stars in our galaxy. And it turns out that in the last few years or so, we've been able to measure the positions and motions of billions of stars thanks to Gaia. And so this mission, while still ongoing, has been really successful at revealing new trends of stellar motions that we couldn't find before this mission, which have very strong implications for galactic archaeology. And so for one of those is the discovery of evidence for an early galaxy merger event that produced an overdensity of stars in the stellar halo, now known as the Gaia Enceladus sausage. And so although it sounds galactically delicious, the Gaia Enceladus sausage is so named because of its appearance in the tomb ray diagram, the diagram on the left here, where essentially you see that the stars have very low rotational velocities on the x-axis, but have a large vertical component in the y-axis that are sort of distributed in this as the blue stars on the left. And you can also see this in terms of angular momentum and binding energy to the galactic potential relative to the sun, which I'm showing here on the right. In addition to kinematics, spectroscopic studies have also identified a distinction between a low alpha element and high alpha element sequence in halo stars. And so this division implies 2 distinct formation environments for different stars in the halo, telling us that some of these stars likely formed outside of our galaxy. The spectroscopic distinction has now been revisited by other surveys, such as apogee, and even more recently, comparison can actually be made between multiple large spectroscopic surveys, where you see that these sort of two sequences in the low metallicity, high and low alpha regime remain. So we still have these two origin stories for our halo stars. Okay, so now that we know we can see this in kinematics, we can also see it in spectroscopy. So what can TESS actually do for galactic archaeology? And the most straightforward answer to that is what we've been talking about for this whole session, which is asteroseismology. It has now been shown that using TESS data for stars near the beginning of the red giant branch of stellar evolution, TESS can measure the asteroseismic bulk properties nu max and delta nu, and combining this information with parallaxes from Gaia, we can constrain stellar ages quite well, which are crucial to determining the formation history of the galactic substructure and the Milky Way as a whole. And eventually, TESS will allow this for the measurement of ages of thousands of stars, which other folks will talk about later at this conference. However, the detailed processing of all of the data that's required to do that can be very time consuming. And so to get around that, University of Hawaii grad student and NSF fellow Nick Saunders and I have been able to turn a target list of TESS amenable giant stars into light curves using a lightweight light curve pipeline called GIANTS, which downloads full frame images of cutouts of our stars using TESScut, stitches all available sectors of data together, and then smooths and cleans those data so that we can do transit and asteroseismic analysis. And we then, produce a summary plot, which we can search for targets or for signatures of planet transits and stellar oscillations. And while I'm talking about planet transits, I just want to highly encourage everyone to check out Nick's talk tomorrow during the ultra short period planet splinter session, starting at 9:30 Eastern time. We've used this GIANTS pipeline to make some really exciting discoveries of planets orbiting red giant stars that you won't want to miss. And even if you don't care about stars or planets, I'm sure you want to know whether Kepler was murdered. Maybe the TESS architects have a little bit more insight into that. But BuzzFeed actually hasn't covered all of the planet science that the GIANTS pipeline has made possible. So Stephanie Yoshida, who will be starting her undergraduate career at Harvard College next month, has been searching these stars for planet transits and has placed upper limits on the occurrence rates of hot Jupiters around halo stars observed by TESS. And this let us predict the number of stars that need to be searched with Gaia and TESS in order to find a transiting planet with an extragalactic origin. This would be a very exciting discovery, but based on this work, I'm not too surprised it hasn't happened yet. Stephanie's poster should be available for the rest of the conference, so check that out. But pivoting back to our TESS light curve pipeline, GIANTS also outputs fast Fourier transforms or power spectral density measurements for all of the light curves in our sample as well. And so that means that even when we couldn't identify a planet, we could identify stellar oscillation signatures to measure precise stellar parameters. And for the sake of time, I'll skip this, but you guys sort of have already heard about nu max and delta nu. So that's what we were measuring for all of the red giants in our sample. And here I'm just showing the stars which we studied more in depth in color. I've color coded them based on their kinematic subgroups, where green stars are those which appear to be part of the disk, while orange and red stars are part of the galactic halo, where these red stars have motions that suggest they're members of the Gaia Enceladus sausage subpopulation as defined by previous work. And furthermore, half of these stars also have spectroscopic data, which aligns perfectly with our kinematic definitions. Orange stars appear consistent with the in situ halo population, whereas the Gaia Enceladus sausage stars are consistent with the low alpha population, like we expect. Okay, so now we have a population of stars with spectroscopic, kinematic, and asteroseismic constraints, and the only thing left to do is determine stellar ages. And so using the 2-mass K magnitude, the Gaia parallax, the TESS input catalog effect of temperature, metallicity where available, and regular large frequency spacing delta nu for each star, we compute the age of each star using 5 different packages listed here. And this gives us ages and uncertainties for all the stars in our sample, which we then represent as a sum of age posteriors. And so digging into this a little bit more, here I've broken down the stellar sample where all the stars in our study are shown on the left, whereas those only with spectra are shown on the right. The vertical dashed lines correspond to the median of each combined age posterior, where the solid lines correspond to the 16th and 84th percentile in those distributions. And so based on this, you can see that there are pretty large changes depending on which age package was used that are larger than the changes between the spectroscopic versus overall population. But in general, we find that the age of the Gaia Enceladus sausage seems to be around 8 plus or minus 3 gigayears, with a systematic difference of about 1 gigayear between age packages. Furthermore, I want to pay close attention to the results from Basta and Param, because those have been tested most extensively with red giant stars, and qualitatively, they seem to agree well. Conversely, we'll note that on the bottom, the scaling giants results are sort of offset. And that's basically also what we expect, because that method was not designed to be used for low metallicity stars. And so overall, even though the absolute ages aren't super robust, the age rankings appear to be robust for these stars. And so we can then use the individual likelihoods that we've actually calculated to determine a hierarchical population age and age variance for each subpopulation of the stars in our study. And as only the isochrones code gave us the direct access to those likelihood samples, we use that to basically determine our hierarchical age populations. And I'm showing the ages that we found here at the bottom. We find again that the Gaia Enceladus sausage is roughly 8 plus or minus 3 gig years old, whereas the in situ halo population appears slightly older, and the galactic disk population has a very broad age posterior, again, as expected. But of course, it's important to have independent confirmation of these age distributions. And even if the TESS team is a suspect in Kepler's murder, we haven't quite succeeded yet. So concurrent asteroseismic studies of Kepler data of this Gaia Enceladus sausage have revealed similar age distributions for these stars, which show that the Gaia Enceladus sausage has a median age between 7 and 10 gigayears, and the in situ halo stars are slightly older. Taken together, these studies seem to be pointing to a merger that happened less than 10 gigayears ago. But again, I'll point out that the absolute ages of these stars and thus the timing of that merger event is really hard to constrain. And since I'm tight on time, I'll just put up my summary slide and thank everyone for listening and take your questions now.
Thanks a lot, Sam. In fact, you are good on time. So we have definitely time for a few questions. So the first question from Monica Djokovic. How did you determine to which galactic subgroup each star belongs?
So the way that we determined that is essentially going back to this plot here on the right. So the red and black lines are essentially the definitions of the Gaia Enceladus sausage from the Helmy et al. 2018 paper and the Koppelman et al. 2019 paper in black and red respectively. And essentially we said if stars fall into that blue box, they're Gaia Enceladus stars. And if they fall outside of it, then we determined they were halo stars. And then based on the tomb ray diagram, we made that division between halo stars and disk stars.
Okay, so I have a question also. The difference between Kepler and TESS, independent on who murdered who, but I mean, TESS is much shorter and stars are much brighter. Could you just say what is? I mean, did we get much more from Kepler, or would we actually just have survived with the same type of data in this direction, or what do we get from Kepler essentially?
Yeah, so the main benefits that Kepler has over TESS is first the 4-year baseline, as opposed to only 1 month or at most 1 year for these stars. Having that long baseline is really important for measuring those stochastic oscillations of the stars, and so the TESS extended mission will be really great for that. The other big difference is the sort of precision of the two telescopes. Kepler was sensitive to stellar oscillations in red giants down to magnitudes much fainter than TESS is, at least right now. But that is also like highly variable, depends on sort of the field that the star's in, how many background stars there are, as well as just sort of, did we catch the star at the right time when the oscillations were particularly strong in one sector versus not. And so in general, I think that in the future, TESS is going to be really powerful and is totally going to overwhelm Kepler in terms of what we're able to do with this sort of galactic asteroseismology. But for right now, I think Kepler still has the larger sample for a little while, at least.
Okay. Then there is a question from Jennifer Winters. How did you account for unresolved binaries?
So in this particular study, essentially what we did is we used the GIANTS pipeline to essentially find stars that were well separated from other targets in the field. This was a visual inspection just to make sure that we were finding the best targets that we could have. So we haven't done any sort of direct imaging of any of these targets, but based on the asteroseismic properties, which we can then cross-check with the, say, TESS input catalog, mass and radii for these stars, we're pretty confident that if there were any unresolved binaries, they weren't large enough to sort of change the magnitudes that we measured for these stars.
Okay, thanks a lot, Sam, for this and the answers. We so this is the end of the first session. Thank you to all the speakers for this session. As far as I could see, we were around 300 participants in this session, so which is of course great. There are some messages from the SOC, as far as I have been told. Jennifer, could you take?
Yeah, thank you, Hans, and thank you so much to all of our wonderful speakers for your talks this morning. I'm going to try and keep this quick so everyone can go refresh their tea before they come back for the second half of this session, but just a few quick announcements. After the break, we have our first set of parallel sessions. And so session 1, which will be stellar astrophysics, will continue in this same Zoom room, and Hans will be continuing to grace us with his presence as chair. And then in room number 2, which you should all have a link to in the logistics emails that Avi sent out last week, Ian Wong will be chairing our exoplanets session. And so please choose accordingly when you come back from break. I'll note that Ian's room is now open if folks want to log in and test their screen sharing ahead of time, so feel free to do that. This afternoon, after the big break in the programming, we have our first panel discussions. This is the Exoplanets panel featuring 4 wonderful scientists talking to you about all different aspects of exoplanet science with TESS and chaired by Leslie Rogers. So we encourage you to tune in and catch that. And then this evening, Eastern time, after the main science programming for the day, we have our first kind of TESS adjacent talk. This will be a presentation on how science and art work together to create the wonderful exoplanet travel posters and Galaxy of Horrors posters that many of you have seen come out over the last few years. The thing you should be really excited about is NASA has, for the past many months, been working on a series of mission posters. So I think Hubble and Spitzer have already come out. The TESS poster technically launches on Friday, but we're going to get a sneak peek of it this afternoon when Thalia, Caitlin, and Joby give us a presentation about how it came into being and how the broader set of exoplanet posters has come into existence. So that's it. Trying to keep it brief. Please go and take 5 minutes to refresh your tea, your coffee, come back ready for another round of science, and we'll catch you soon. Thanks.
Thanks, Jennifer. So we will start in 10 minutes, I guess. Slightly late. But. So welcome back to those that stay here in session 3. And we will continue with 4 talks of 15 minutes. And you can see them here. And again, for the questions, we will use the Slack channel. And you should go to Stellar Astrophysics for this. This is the channel we use for questions related to these 4 talks. So first of all, Jackman, you will be the first speaker in this, and I will stop sharing and you can take, please go ahead.
Lovely. 1 second. You can see that?
Yes.
Yes. Lovely. Lovely. Right then. Hello, everyone. I'll begin. Hello, everyone. My name is James Jackman. I'm a postdoc at Arizona State University, and I'm going to be talking to you today about the current disconnect between white light and UV emission from flares from low-mass stars, but specifically the disconnect between the UV predictions of empirical flare models that have been calibrated using white light observations. So firstly, what is a stellar flare? So a stellar flare is an explosive phenomenon caused by a reconnection event in the magnetic field of a star. Field lines come together, and they reconnect, releasing energy. This accelerates charged particles down towards the chromosphere, which then heats plasma, resulting in emission. But the whole flare process releases energy across the entire electromagnetic spectrum, from radio all the way up into hard X-ray. The highest energy flare we've seen from the modern sun was the Carrington event in 1859 that had a bolometric energy of about 10 to the 32 ergs. But when we look at low-mass stars such as M dwarfs, we typically see flares with energies tens, hundreds, or even thousands of times greater than this, and they can occur on weekly to monthly timescales. So why might we be interested in flares? Well, in particular for exoplanet habitability, we're interested in their UV emission. In the near UV, flares may be beneficial to life on rocky planets around low-mass stars, such as the ones that we're looking for with TESS. The near UV flux could provide the near UV flux from flares could provide the energy for pre-Bartic chemistry to occur on the surfaces of these planets, chemistry such as the formation of lipids and amino acids. These cool stars may not provide enough of this flux in quiescence, and flares could provide it on a stop-start basis. At the same time, the far UV flux from flares may destroy biosignatures. It may exacerbate atmospheric evaporation and ozone depletion. So we need to know the exact balance of these 2 effects. But also, if we want to understand the long-term habitability of these planets and their atmospheres, we need to understand UV flare rates. So the distribution of flare energies, so how often different flares of different energies occur. And if you want to measure a UV flare rate for a particular star of interest that you found, there's something in the chat. For stars that you found, then you need to look at the stars with instruments such as these, Hubble and Swift. However, measuring UV flare rates requires detections of many, like tens upon tens of flares, requiring tens upon tens upon tens upon tens upon tens of orbits with HST, which is a very time-consuming and expensive thing to do. So, is there some way we could get around this to constrain the UV flare rates of these stars? Well, one idea thrown around in the literature has been to use white light flare rates measured from TESS and use these to calibrate empirical flare models that we can extrapolate into the UV. So we all know that TESS obtains wide field and long baseline observations, such as these, where this is a light curve, a detrended light curve of a early main sequence M dwarf, where each one of these spikes is an individual flare. So if you zoom in, you can see some flares there. If you assume an empirical flare model, such as a 9,000 Kelvin black body, which is a pretty standard one used in flare literature, and itself is based on optical spectroscopy of flares from active M dwarfs. If you calibrate the ratio of your model and the quiescent spectrum within the TESS bandpass, and you calibrate it to the amplitude of the flare in your given light curve, then you can get a calibrated flare model, which you can then integrate over all wavelengths to calculate the bolometric energy of a flare. If you do this repeatedly for every flare you detect in your publicly available TESS light curve, you can calculate a bolometric flare rate, such as the one shown on the right-hand side here, where on the y-axis is the number of flares above a given energy per day, the x-axis is your flare energy, the black line is the observed TESS bolometric flare rate, assuming this given flare model, and the green line is a fitted power law. Now, if you know your model, then you'll know the fraction that your model emits in the UV. So you can then use that fraction to predict your UV flare rate. Now, you don't just have to do this using a simple black body spectrum. Other more complex models exist, such as the muscles model from Lloyd et al. 2018, which uses this black body to describe the continuum emission from the heated plasma at the flare foot points, but then includes near UV emission lines and also stitches on far UV spectra taken from HST to incorporate far UV emission lines and also include a heightened FUV continuum. Now, this all sounds well and good. It potentially provides a way of directly predicting UV observations using the plentiful white light data that we already have. However, UV observations of flares are relatively few and far between, and these models have not been tested using UV observations. Particularly, they haven't been tested when they've been calibrated using white light observations. Simple models such as the black body don't incorporate UV continuum or UV lines that in the near UV have been shown to contribute, say, up to 40% of the observed flux. Also, many of these models use single temperatures and don't incorporate recent observations that from, say, in the optical that have found flare temperatures at the peaks going up to 20,000, 30,000, or even 40,000 Kelvin, which can result in not only higher energy flares, but flares that emit more of their energy in the UV. So the UV predictions of these models, we need to test their accuracy if we're going to put them into photochemical models. So how do we go about testing them? Well, as I mentioned earlier, one way of testing them would be to measure UV flare rates for lots and lots of individual stars. But that's a very expensive thing to do and very time consuming, and good luck getting it past the HST TAC. One other option would be to look at archival data, such as with GALEX. GALEX was the Galaxy Evolution Explorer, and it was a UV mission that observed about 2/3 of the sky in the near UV and quite a bit less in the far UV between 2003 and 2012. GALEX observed in a time tag photon mode, meaning that when it got a photon, it was a good one. You knew the position of the photon on the detector, you knew the time of arrival, and you knew the energy of said photon. My colleague Chase Millian in recent years has developed the G-Photon Python package that enables users to create UV light curves from this data. Now, GALEX only observed when it was in the Earth's shadow. So each one of these, your light curves are split into half-an-hour visits. And also GALEX observes such large fractions of the sky, meaning that these light curves have quite sparse time sampling. You might have half an hour here, then half an hour on the next visit, and then you might have another couple of months, and then you might have another half an hour, and that might be it. Meaning, while you have UV light curves, you may not be able to use them really to measure UV flare rates for individual stars. But the fact that GALEX observes so much of the sky means that you can use this data to measure ensemble average flare rates. And another instrument that's observed quite a large fraction of the sky and can be used to measure ensemble average flare rates in white light is TESS. So to test the UV predictions of empirical flare models calibrated using white light data, we've been combining TESS and GALEX observations of about 1,000 early main sequence M dwarfs. These stars had 2-minute cadence observations up to in sectors 1 to 32, just because that was what was available when we started this project. They had at least half an hour of near UV data, and this resulted in about 300 or so that had far UV data as well. We've been testing a variety of different empirical flare models from the literature, but I'm just going to focus in this talk on the 9,000 Kelvin and the muscles models, because those really depict the extremes of what's available on the market. So how do we go about testing these models? Well, first, for each model, we calculate the bolometric average flare rate from TESS, shown here on the right-hand side. We then use our model and use the predicted UV fraction to predict the UV flare rate. Now, we don't just compare the observed average flare rate from the GALEX, say near UV bandpass or the GALEX far UV bandpass, directly to these power laws. Because of that sparse time sampling, we need to take into account, say, the window function and the noise properties of the GALEX data. The half-an-hour visit lengths can result in partially observed flares, which can shift higher energy flares to apparent lower energies, messing around your results. So we performed injection and recovery tests according to these predicted UV flare rates directly into the GALEX light curves to take into account that sparse time sampling. We do this about 10,000 times per star, and then measure artificial average predicted flare rates, and then compare these to the average UV flare rates that we've actually observed. We've done this in the galaxy near UV and the far UV bandpasses. And I'll just a quick model reminder for what the 9,000 Kelvin black body and the muscles model look like. And here are our results from those injection and recovery tests. On the right-hand side, the black line is our observed average UV flare rate for those early main sequence M dwarfs. And the red line is the average predicted flare rate for each model from our injection and recovery tests. And the shaded region is a 1 sigma region in flare rate taken from the results of our injection and recovery. We find that the 9,000 Kelvin model just by itself will underestimate near UV flare rates, or the near UV energies of flares, by a factor of about 15. Now this assumes that every UV flare has a white light counterpart. The muscles model is slightly better because it has these UV emission lines, but it still underestimates the near UV flux in the Galactic bandpass by about an order of magnitude. In the far UV, it's a little bit more difficult to get results out because we had much fewer stars. Remember, we had about 300 compared to that 1,000. The stars are a lot fainter in the far UV, meaning the flares need to be a lot brighter. But we can still try and get some constraints out. So in the far UV, interestingly, we find that our 9,000 Kelvin model doesn't actually register in our injection and recovery tests. We're putting the flares in, but we can't get them back out. The muscles model, which was built with the far UV in mind, remember it's that black body spectrum with the HST far UV kind of stitched on top. It's better, but it still underestimates far UV energies by about a factor of 20. Our running assumption for this is potentially due to the increased continuum temperatures I mentioned earlier that will result in higher energy flares and flares with higher fraction of their UV emission. And the way we're going about testing this at the moment is injecting higher and higher temperature black body flares directly into our near UV light curves and seeing if we can come up with a temperature that best matches the results or best matches our observed UV flare rates. But at the moment, if you're going to try and predict the UV flare rates of M dwarfs using these models, you need to be careful about the predictions that you're making. And with that, I will conclude. Thank you.
Thanks a lot.
Clap for myself. Hey, well done, James.
Good idea. The only one who can. So please type in any questions. This time we use stellar astrophysics and not the one for asteroseismology. So you can type in your question there. While the rest of the participants are thinking about questions, let me ask one. So if you were to design a mission that could actually do what you are missing here, because I of course understand that there are some other data you use, what size telescope UV for the UV would you actually need?
Well, in an ideal world, if I had my own UV instrument, then in an ideal world, I have my own Hubble. But
yeah, but could you survive with less than Hubble? That's my
question. So in fact, there are a couple of missions on the horizon that will be able to do this work. So importantly, what we really need is simultaneous optical and UV kind of photometry and UV spectra. And there are a couple of missions actually being led out of ASU by my boss, Evgeny Shkolnik. Sparks, which will get near UV and far UV photometry, which will be fantastic for this work.
Yeah.
And then UV scope as well, which will get spectroscopy. And I think the ESCAPE mission as well, and maybe CUTE as well. So there are already missions on the horizon that will provide this simultaneous UV, well, when combined with a mission like TESS, will be able to provide this simultaneous UV and optical observations for a large sample of stars.
Okay, then we have a question from Yuta Notsu. Good talk, James. Any suggestions of future modeling UV emissions of flares? For future UV emissions of flares, yes.
Yeah, so for future modeling of the UV emissions, if you're trying to calculate, so this is what we're trying to do at the moment. If you're trying to calculate flare energies, we're trying, this is why we're putting in hotter and hotter black body temperatures to see if there is maybe some black body temperature that can simultaneously match what we see in the TESS bandpass and what we see at least in the near UV. Another factor as well that these models don't incorporate at the moment, which I think is work being led out of Colorado or highlighted by members at Colorado, is the incorporation of the Balmer jump as well. A lot of these models don't incorporate the Balmer jump, which contributes quite a bit in the near UV. I think Adam Kowalski in 2019 led a study that found that if you normalize the 9,000 Kelvin black body to the continuum around the Balmer jump, it'll underestimate it by a factor of 2. So at the moment, yeah, I would wait and see what we come up with the higher flare temperatures, but consider for the UV potentially just calculating the energies just in the UV by themselves. Yeah, I haven't got a exact model off the top of my head, but I will think on that.
Okay. Good. You can of course answer this maybe on the Slack. And there's another question there on the Slack, so you can go there. But thanks again, James.
Lovely. I'll stop sharing.
Then next speaker is Elsa Palumbo. So Elsa, you can take the screen now. Please go ahead.
Let's see, is this showing up okay?
Yes, it's perfect.
Excellent.
And I hear you clearly. So.
Hi, everybody. I'm Elsa Palumbo. I'm a rising junior at Caltech. And today I'm going to tell you about some interesting magnetic activity that's going on around a young M dwarf that I discovered last summer. Before I get to any of that, though, I'd like to start with just a little bit of background. So as many of you may know, young stars tend to be pretty magnetically active. And by that, I mean that they usually have relatively strong magnetic fields, and that things like star spots, stellar flares, and coronal mass ejections often occur pretty frequently. A bit less well known, though, is that around stars with especially strong and stable magnetic fields, a centrifugal magnetosphere can form. And when that happens, the stellar wind, instead of escaping away from the star like it does around the sun, will actually start to accumulate in dense clumps at the co-rotation radius. These dense clumps are called magnetospheric clouds, and when a little bit of dust gets mixed in with the plasma, these can actually appear as optical dips in the light curve. Now, magnetospheric clouds are made up of ionized material, which is why the star's magnetic field lines can keep them constrained to the centrifugal magnetosphere. Now, the thing about magnetospheric clouds is that they can't keep on growing forever. And I say that because at a certain point, they will reach a critical mass where they're so heavy that the star's magnetic field lines can no longer constrain them. So this means that there must be some sort of mass balancing mechanism, some way for material to escape away from the centrifugal magnetosphere. And in the literature, the first mass balancing mechanism that's been discussed is called centrifugal breakout, and that was introduced by Townsend et al. In 2005. Now, the way this would work is that as soon as this critical mass is reached, the magnetic field lines constraining the plasma would snap, the material would spew out, and then the field lines would suddenly reconnect again. Now, all this might seem sensible enough, but there is a bit of a catch, which is that for about a decade, astronomers have been looking for evidence of centrifugal breakout around the high mass stars that the theory was originally developed for, but without success. One especially high profile non-detection happened in 2013. That was by Townsend et al. Around the star, B-type star Sigma Ori E, whose light curve I've shown right here. And after this non-detection happened, many astronomers started to reconsider whether centrifugal breakout was an important mass balancing mechanism in the first place. But in a paper that my co-authors and I just submitted for publication a few weeks ago, we argue that the reason for these non-detections may not be that centrifugal breakout is unimportant, but rather that astronomers have been looking for evidence of it around the wrong type of star. So these massive stars instead of young M dwarfs. Now, part of my reason for saying that is this star, TIC 234. And the really interesting thing about this star is that it has this transit-like dip, which is co-rotating, and that's present in a whole sector of TESS data, but that then suddenly disappears in a matter of just over a day, as you can see in this plot right here. And when I say this, your first thought might be, oh, maybe there's a partially dissipated protoplanetary disk, maybe this is a Dipper star, but our data doesn't seem to support that conclusion because the spectral energy distribution of our target does not show any infrared excess. So on TIC 234, we have three sectors of 2-minute cadence test data. And this allows us to see a number of interesting but rather puzzling characteristics. So first off, in the year between TESS sector 1 and TESS sector 27, we see a phase change, even though the dip appears to be co-rotating. Also, throughout sectors 1 and 27, we see gradual changes in the duration and depth of the transit. And as I mentioned before, the dip disappears from near maximum size to nothing in just over a day, and that is absent for all of TESS sector 28. The TESS data also gives us a couple other clues. One of them is that the variations in transit size appear to be gradual, which is in contrast to what we might expect from, say, a disintegrating planet. And we also, right around the time when the dip disappears, we also see a sudden brightening event, which we don't think is a flare because it's too symmetric. It doesn't have a steep rise in exponential decay like we would expect from a flare. Also, right around the time when the dip disappears, we notice that the rotational amplitudes, which we take as a proxy for spottedness, are larger. And just a few days after, we see this 120% flare. So we take all that as evidence of increased magnetic activity right around the time when the dip disappears. Besides our TESS data, we have information from a few other sources, and these give us more clues about what might be going on in the system. First off, we have photometry from the Las Cumbres Observatory, LCO, and that tells us that the dip actually returns about 100 days after the end of sector 28, when the dip was entirely absent. Also, we have photometry from Assassin, which covers about 4 years, although it has rather low cadence, but that's still enough to confirm that the star's rotational signal appears to be stable over timescales of years, and we infer that the same is true of the star's magnetic field. And this is an important thing because that is one of the prerequisites for forming a centrifugal magnetosphere. Finally, we have spectral data from the Veloce Rosso spectrograph, and that shows that the H alpha line is actually stable in shape over phase. And this is important because we would not expect this if, say, the dips were being caused by secondary eclipses of slingshot prominences that are emitting in the hydrogen lines, because in that case, we would expect shape changes due to the Rossler-McLaughlin effect. So the story that we do think makes sense for our system is a magnetosphere, cloud, and centrifugal breakout model. And much of the reason why we think that this is a good fit is that our data seem to match the predictions that Townsend et al. Made about 15 years ago. So first off, the fact that we see depth variations in the dips is not surprising, especially the gradual increase in size up through sector 27 before the dip disappears. Also, the sudden disappearance of the dip from near maximum size is exactly in line with the predictions of centrifugal breakout. Plus, a magnetic reconnection event is expected to immediately follow breakout, and we think we might be seeing the optical signature of that via the flare-like event that I was discussing earlier. Part of the reason why we think that's plausible is just the timing, but also Stauffer et al. In 2017 observed some similar unusually symmetric flare-like events that happened at state transitions. Also, the fact that we have evidence for the dip returning, direct evidence via the reappearance in the LCO data, and also indirect evidence via the phase change between sectors 1 and 27, that's entirely consistent with what this model will predict. And finally, the increased magnetic activity that we see surrounding breakout is exactly what we would expect as well. So this story we have answers quite a lot of our questions about the system, but it also leaves a few things unanswered. Most notably, how exactly is this material getting into the centrifugal magnetosphere in the first place? And so far, I've kind of been waving my hands and saying, oh, stellar winds. But the thing is that the theory for centrifugal breakout was developed in the context of massive stars. And it's not clear that this is still a plausible mechanism that low mass stars would have strong enough winds. So in our paper, my co-authors and I suggest that coronal mass ejections might be a plausible mass feeding alternative for low mass stars. And we say this both because this would be a way to suddenly deliver a large amount of material to the magnetosphere, and because there's a bit of a theoretical basis for having coronal mass ejections trapped in the magnetospheres of low mass stars, as in Alvarado Gomez's work in 2018. This also could possibly explain why we might observe centrifugal breakout around low mass stars, but not around high mass stars like Sigma or E. So that said, the TIC 234 is really interesting also because it seems to tie together a whole class of young low mass star systems with unusual variability. All of these seem tied together by a number of characteristics, some of which I've listed here. But TIC 234 really stands out, and that's both because of the direct evidence it gives us for centrifugal breakout, but also because it's the brightest of the bunch, which makes it a really great choice for follow-up photometry. And also because TESS's long baseline has allowed us to study the long-term evolution of the system. So with that, I'd like to thank everyone who has helped me with this project and to get to this point. Are there any questions?
Thanks a lot, Elsa, and perfect timing. Please type in any questions to the Slack. While we're waiting for questions, I would like to ask one. So you say here actually in the end that this represents a whole class of stars, and this is the brightest one. But have you seen other phenomena in other maybe slightly fainter stars that are very similar to this, or is this phenomenon you see here unique in this light curve?
So I think that people weren't always clear that that centrifugal breakout was what was happening. But in retrospect, I think we do see this happening in some of these fainter stars. So the events that Stauffer et al. 2017 called state transitions, I suspect are breakout events. Plus, when we see phase changes in the dip around PTFO, I also think that that's due to centrifugal breakout events. But that hasn't always been recognized in the literature, I think. This is
okay. Yeah. So based on what you know now, you can of course go back and see lower signals to noise, but identify them correctly. Okay. So the way TESS will observe in the future, will that be good? Also staying, I mean, for example, yeah, the observing modes, will that be good for finding more candidates?
Yeah, I expect it will be. I think also now that we just have an eye out for looking around low mass stars, that's a large part of the battle. So, okay.
There's actually a question related to this asked by Vicky Antocci. A very nice and interesting talk You have additional candidates from the Kepler data. It's similar to maybe what I asked, but from the Kepler data. Have you seen the search for that in the Kepler data, or is that are there any in Kepler that can be useful here?
I'm not aware of any at the moment, but I would be very interested if anyone here had any to suggest. I would definitely like to take a look.
Okay, there's then one from James Davenport, a really fascinating system. Any thoughts why we don't see these around every rapid rotating flare star? Are they so rare in time?
Okay, so I think part of it is that, so rapid rotation isn't quite sufficient. You also need to have a very stable rotational signal and stable magnetic field that needs to be sufficiently strong. So that's part of it. Part of it might also be geometric effects. Yeah, and otherwise, it's part of, this is kind of going into speculation, but it might have something to do with what types of stars are giving off CMEs and which ones can be trapped in the magnetospheres. So.
Okay. There are more questions on the Slack, and I suggest you go there and maybe thanks a lot, Elsa, again. And then next speaker is Kosuke Namekata, and you can take the screen now. Please go ahead.
Okay, thank you. Can you see my screen?
Yes, and hear you.
Good evening. It's midnight in Japan. So my name is Kosuke Namekata. I'm a postdoc at the National Astronomical Observatory of Japan. So first of all, I'd like to thank organizers for giving me a chance to talk in this session. Today, I will talk about our study, the detection of the filament eruption from our superflare on a solar type star. So let me start from the basic introduction of the solar and stellar flares. And solar and stellar flares are the sudden brightenings on the solar and stellar surface, which can be seen from the X-ray to the radio wavebands. So in the case of the solar flare, the energy is ranging from 10 to 29 to 10 to 32 ELG. But on the other hand, in the case of the star, such as M dwarf, the stellar flare energy become up to 10 to 35 ELG, which is called the superflare. So the left panel shows the schematic picture of the solar flare and the coronal mass ejection. And in the case of the sun, solar flare produce the cool material eruption called the filament eruption and much high temperature material called the coronal mass ejection. And they sometimes affect the planet and Earth environment. And by analogy, it is expected that exoplanets around active stars can be much more severely affected by the stellar flare, stellar superflare, and super mass ejection in the form of such as the high energy particle and atmospheric escape and the generation of the prebiotic chemistry. But its effect is little known so far. So in this decade, Kepler Space Telescope opened a new era in the stellar flare physics. And one of the big surprise on the Kepler is that not only the cooler dwarf, such as M dwarf and K dwarf, but also the young and old solar type G-type main sequence stars shows the very large flare called the superflare. This is published in the Maihara et al. Nature paper, and this is right curve of the Kepler right curve of the superflare on the solar type star. And recently there is a growing interest in this superflare on the solar type star from the viewpoint of its impact on the exoplanet atmosphere around the young sun, and whereas as a proxy of a possible superflare on the current our sun. So there is a Kepler's homework. There is still an open question that the superflare on the solar type star can produce a very huge mass ejection or not, and whether it can affect the exoplanet or not. Actually, the Kepler target was very faint, and there is no simultaneous observation of the spectral line during flares. So in order to investigate the mass ejection and its effect on the planet, the spectroscopic monitoring observation of the active solar-type stars, hopefully with simultaneous Kepler level photometry, is very important to make a progress from the Kepler era. So now we have a TESS, and there is two big advantage of the TESS in this field. The first is the high precision photometry, like a Kepler, which can detect the superflares on solar-type stars whose amplitude is too low to detect from the ground. The second advantage is that the target star is very brighter compared to the Kepler target, which enable the simultaneous spectroscopic observation of flares from the ground. So our approach is to conduct the simultaneous observation with TESS photometric observation and the ground-based spectroscopic observation, optical spectroscopic observation. We consider that the optical spectroscopic observation will be able to detect the cool filament mass eruption as indicated here. And TESS photometry is very important to confirm the fast detection of the optical spectroscopic data of the solar-type stars flare. And as well as to know the energy release and the spot evolution. This is our observation summary. Our target star is an EK Dora, which is known as the very famous young solar analog in the main sequence. And this is also one of the most active solar-type star in the northern field. And we have conducted the simultaneous observation with TESS photometry and H-alpha spectroscopy from the ground. And we use the Japanese two ground-based telescope. The first is a 3.8 meter semi-telescope, and the second is the 2 meter Nayuta telescope. And we have conducted the H-alpha, a time-resolved H-alpha spectroscopic observation with high S signal to noise and high cadence. So this is a simple summary of our result. And we have conducted a very long time baseline about the 32 night, which is very big campaign for only one target star. And finally, we have detected two stellar flare in this Ikedora with the H-alpha and TESS. And I will introduce one very interesting event today. So this is a light curve. And here I'm plotting the light curve of the detected stellar flare in the TESS and the H-alpha equivalent widths. And as you can see, there is a small but significant H-alpha flaring emission was confirmed by the simultaneous TESS white light flare. The amplitude was very small, but thanks to the TESS photometry and large mirror ground-based telescope, we have detected this small amplitude flare. So this was the first confirmation of the optical spectra of the superflare on solar-type star. So we have calculated the barometric energy of the flare from this TESS light curve, and the flare energy was about 20 times the largest solar flare, which is classified to the superflare. And one of the biggest surprise in this observation is that there is post-flare H-alpha dimming after the flare for about 2 hours, although there is no dimming in the TESS white light. So this may mean that some cool material appeared just after the energy release of the flare. So let me show the spectra of the H-alpha spectra of the flare. So the right panel shows the pre-flare subtracted H-alpha spectra in the impulsive phase and the post-flare phase. And here is the right center of the H-alpha. And as you can see, there is a significant blue-shaded absorption component in the post-flare phase with the velocity up to 500 km per second. This indicates that there is some cool material is lifted from the star. And we could detect the temporal evolution of the peripheral subtracted spectra. And bottom is the spectra in the plane of the time and the wavelengths. And here is the line center. And we are now showing that the blue shielded component gradually slow down in time. And we found that the deceleration of the blue shielded component was very consistent with this Ikedora's surface gravity. So this observational feature is very similar to the solar filament eruption, which is often observed in the H alpha. So by this, based on this observational fact, we concluded that we detected stellar filament eruption on the solar type star for the first time. So let me discuss 3 points for this filament eruption. The first, where is the filament erupted from? The TESS also show the much longer baseline observation right curve, and this is a global right curve of the TESS of the Ikedola obtained from the TESS. And the superflare we obtained was observed here. And there is a rotational variation with large star spot is observed in this Ikedola's right curve. And it is found that the superflare and filament eruption we detected occur around the local maxima, which is not the dominant spot in the surface, this indicates that the filament eruption originates from the much smaller spot group compared to the dominant spot. So this may indicate that the filament might be easy to be erupted and without being suppressed by the strong magnetic field of the large dominant spot. Second, let me discuss about how fast it was. So the maximum velocity we detected of the filament eruption was actually very faster than the typical solar filament eruption, whose typical velocity was 10 to 400 km per second. This right panel shows the comparison of the solar filament eruption and the stellar filament eruption in the plane of the velocity and the length scale. And this figure also shows that the superflare has very large length scale and large velocity compared to the solar filament eruption. And in addition, in the case of the solar filament eruption, and outer coronal velocity, which cannot be seen in the H alpha, is typically 2 or 8 times larger than in the velocity and than the filament eruption. So this solar observation may indicate that a possible stellar coronal mass ejection, which cannot be seen in the observation, can lead to much larger velocity, for example, 1,000 km per second or 4,000 km per second, which is very large. Finally, let me discuss about how huge it was. So we confirmed that the filament mass we obtained was 10 times greater than the largest solar mass ejection. So this may indicate that young exoplanet system or young solar system around the young sun can be much more severely affected by the mass ejection than we experience in the current sun. And in addition, we found that the erupted mass and the TESS bolometric energy was found to be on the solar observational and theoretical scaling relation. So these findings may indicate that the properties of the stellar filament eruption and possible CME on the solar type star can be understandable or predictable by the solar physics simply. So this is a summary and future work. So our detection of filament eruption from a superflare on solar type star will give the first opportunity to estimate its impact on the exoplanet environment around the young sun. And thanks to the TESS high precision photometry, and the small amplitude HR for flaring emission and absorption component was firstly confirmed. And the relation between the filament eruption and the flare and spot configuration was obtained. As the future work, we would like to find the X-ray and UV and radio signature of the stellar mass ejection simultaneously with the ground-based observation and the TESS photometry. And the TESS predetermined schedule enable the coordinated observation from the other ground-based and space-based telescopes. And we wish to do much more longer term observation to provide the statistical properties of the stellar mass ejection on solar type star. And finally, so this kind of the statistical approach will be able to will enable us to estimate its impact on the exoplanet environment and the stellar evolution. So that's all. Thank you so much.
Thanks a lot. We have time for at least one question. So David Ports ask you, do you think the size of the filament could cause a pre-flare dip if the orientation was just right?
So thank you for asking. So actually, we could not the pre-existing filament material in this observation. And actually there is a very long pre-flare phase observation, and there is the HR4 component was very, very flat in the pre-flare phase for about 2 hours or 3 hours. So maybe if there is some pre-existing filament material, we may be able to detect, but in the case of our observation, we could not detect it.
Okay, thanks a lot. There are more questions on the Slack. Please go there, but thanks again for
Thank you so much.
Then we have the final talk by Bálint Seli. Please take the screen and start.
Okay, so is this visible?
Yes, it's fine.
Okay, so hello everyone, and thank you all for having me here. My name is Bálint Seli. I'm a PhD student at Concoli Observatory, and today it's my pleasure to present you the result for photometric analysis of ultra-cool dwarfs that was made possible by the TESS full-frame images. At the start, let's review what we know about these ultra-cool dwarfs. So these are objects with spectral type M7 or later. So these are around the stellar substellar boundary. So actually some of these objects are prone dwarfs. They are all fully convective and therefore possibly magnetically active. And since they are so faint and small, they're quite challenging to observe with any kinds of instruments. The most notable example of ultra-cool dwarfs is TRAPPIST-1, which is a nearby system that hosts 7 terrestrial exoplanets, 3 of which orbit inside the habitable zone. And this system is of prime importance for exoplanet habitability studies. And for those, it is really important to characterize the magnetic activity of the host star, because it can influence life on the exoplanets. So to gain some insight about the photometric activity of TRAPPIST-1, we wanted to observe it with TESS. So let's see where it lies on the sky. Unfortunately, TRAPPIST-1 is near the ecliptic. So the first year of the TESS mission missed it, and so did the second year, and so does the third. However, the fourth year of the mission will be centered on the ecliptic, but if you zoom in, you can see that it sits just in between the CCD cameras, so it won't be observed with TESS. But we really wanted to say something about its magnetic activity, so instead we thought we'd do an ensemble analysis. So instead of observing just TRAPPIST-1, let's compile a sample of similar stars, similar in some respect, and then say something on average about their magnetic activity properties. To construct this sample, we used really simple criteria. We plotted TRAPPIST-1 on the Gaia color magnitude diagram, drew a circle with half a magnitude radius, and all the stars within this circle become part of our sample, provided that they're closer than 50 parsec and they satisfy some Gaia quality cuts. Overall, we had more than 300 of these objects, with more than 200 of them being observed in the first 2 years of the TESS mission. Here you can see their brightness distribution, and since the Gaia RP band is close to the TESS passband, you can say that most of these stars are brighter than 17 magnitude, which is still pretty challenging considering the nature of the variability that we're looking for. As an illustration, here are two stars with similar brightness. On the upper panel, you can see a Cepheid from the Large Magellanic Cloud, and while it's an extragalactic variable, you can clearly see its pulsation, even with the 10 centimeter TESS. And on the lower panel, you can see one of our targets, and the light curve looks like a noisy mess. However, if you do a careful period analysis, you can uncover its rotational signal, and you can also identify a possible stellar flare just in the middle. So this is what we are interested in this study. So to do this, after compiling this target list up to sector 26, so the first 2 years, we run the QD-LPX pipeline, which is to extract light curves from full-frame images. It uses FIT-SH with convolution-aided differential photometry, and it is designed to work for even fainter and more contaminated targets. However, since some of our stars are in really dense regions of the sky, we needed some extra contamination removal, and for that we used principal component analysis on the light curves of nearby stars. So we run PCA on high-level science products, so not pixel data. And after this, we just did the usual Lomskargil period search and flare detection. Now, as an example, on the left panel, you can see one of our targets marked with the red cross in the middle. And you can see that in its neighborhood, there are quite a lot of brighter stars. And the grid in the background illustrates the pixel scale of TESS, so we can expect some sort of contamination from those. To mitigate this contamination, we selected those additional apertures marked with the circles and extracted their light curves as well, that you can see on the right. And we use these light curves for PCA. And with that, we constructed the light curve that you can see on the left with orange. And after subtracting it, we're left with the clean data set where you can actually see some rotational modulation. And here, if you do Lomskargil period analysis, you can see that it's around 2 days for this star. And now onto the results. We managed to find rotational modulation in 42 of these stars, but we only looked for periods below 5 days. And that's because there's so low amplitude that we're expecting that any longer period would make detection so ambiguous. But what you can see here on this logarithmic distribution is that it looks more or less like a Gaussian and unimodo. And it might not be that affected by that 5-day cutoff. We can actually compare it to other distributions for the literature. So here I cherry-picked just a few of them. And the most striking feature is here that M dwarfs come in 2 types. There are the fast rotators, like the ones in our sample, and there are the slower rotators with periods ranging from tens to hundreds of days. And that's not too many objects in between. And there is especially where our 5-day cutoff is. So we can say that it shouldn't actually bias the fast rotator distribution that much. Okay, and now another thing, we wanted to have as many age estimates for this star as possible. And this is not easy because these most of the methods don't really work for these low mass objects, but there are still some to work. We used galactic kinematics, so we used galactic space and velocity components to reveal the age probability density function of these objects. And actually, albeit with high error bars, we could have age constraints for 71 of these targets. 12 of these stars were parts of nearby moving groups, so pinning down their ages quite precisely was a good thing to add. And we also looked for co-moving pairs with Gaia, managed to find 5 where the pair itself had some sort of age estimate that we could use. And we also looked for lithium absorption in the resource spectral library, but managed to find none. So this only puts a few lower limits on ages, but overall we had 88 of them. And here you can see the distribution, but don't get your hopes up. The error bars are pretty huge. So if you'd see them propagated into this distribution, yeah, don't you really want to see that. But now we can search for some possible correlations with the stellar age. On the left, you can see rotational period versus age. And while there might be some weak correlation, it is not really significant, but that might just be because of the high errors on stellar age. And on the right, you can see hydrogen alpha equivalent width versus age, where it was measured from the resource spectral library again. And there's quite a lot of scatter here as well, but we could argue that the activity of these stars is saturated, so the rotation rate or the age no longer influences the hydrogen alpha emission. Okay, and the last thing we did with this light curve is to search for stellar flares. But because the noise level was quite high for all of these data sets, we couldn't use any of the fancy sophisticated flare detection methods, so we resorted to simple manual letting. And overall, we managed to find 94 flare events. Here you can see the three most flaring stars from the sample. And after correcting for the recovery rate or the completeness, we created flare frequency distribution for the composite sample, so for all of the targets combined. And that is what you can see here. A flare frequency distribution is just the cumulative number of flares per energy, but the flare energy can be estimated as the time integral of the flare, so the area under the light curve, multiplied by the quiescent stellar luminosity. With gray and black points, you can actually see the FFD of TRAPPIST-1 itself from the Kepler K2 light curve. And with orange, you can see the stars from our sample. And once we fitted these with power laws, we got similar power law indices around 2, which is pretty typical for these types of stars. And what is really nice is that these two FFDs seem to lie in a continuation of each other, which means that the flare frequency distribution of TRAPPIST-1 can actually be extended to 1 or 2 orders of magnitude higher energies. So if for any kind of habitability study for TRAPPIST-1 you need a super flare rate, you could just extrapolate the FFD you already got. And that actually marks the end of what I wanted to say here. So let's just quickly summarize the results. So it seems that in terms of rotation period and flare activity, TRAPPIST-1 is just an average or ordinary star for its spectral type, which is really nice because TRAPPIST-1 will have extensive follow-up in the future. And it's good to know that anything that's uncovered for this single object could be extended to a much larger sample of stars. And as a future prospect, that's now the present, the TESS full-frame images are now acquired with a 10-minute cadence. So it's 3 times better than what we had here. And it will make them much more suitable to find stellar flares. So stellar flare won't just consist of 2 consecutive data points, but like 6 or so. So it will be something to look forward to. And with the end of year 3, it's now the prime time to do some homogeneous flare studies with full-frame images. So that was all I wanted to say. Thank you all for your attention. And if you're interested about the details, check out the full paper online. So thank you.
Thanks a lot. Then please type in any questions into the there's one here from Stephanie Retz. How did you correct for the flare completeness?
Yeah, that's a great question. There was a little cheating there because we identified flares manually, but for completeness tests, that's just injection tests. So we injected flares with different energies and tried to devise a detection method that's similar to what we'd see. It's simple, just 2 and 1 sigma of the consecutive points. And that gave something similar to what we wanted. So here we reanalyzed the Kepler K2 light curve and also the light curves we had. So that is why there are two of those. So these completeness curves look like sigmoids, and we calculated them from all those light curves we had, and they took the average and used that single correction curve, and that induced these large confidence regions here. So that might not be that appropriate, but fitting it could take into account.
Okay. You mentioned the faster cadence for FFIs, but according to George Stricker, it will even go down to 200 seconds. Could you just say what is how much do we benefit in the studies of flares when you go from 30 minutes down to 200 seconds?
Well, for these stars, the problem is that they are faint. So if we have better cadence, we have higher noise. So that's a problem, but it will be great. So much more data points would result in much greater detection efficiency for flares. And for rotational periods, I believe the shortest we got were 0.1 days, so 2 or 3 hours. Maybe there are faster rotators, but I'm not sure about that.
Okay, so actually related to this, you showed the fast and slow data plot, of course, and of course it's not, that's the distribution of all these type of stars. What is actually the reason for this difference?
Well, that's an excellent question. As much as I understand it, it's the stellar evolution models could say something about it for higher ages. So as far as I know, when stars are born, they are rapid rotators mostly, and then there are these two populations. But there are stars with all kinds of ages in this sample, so that might also have an effect here.
Most of these stars, I guess, are still not very evolved, of course, because they evolve so slowly. Okay,
yeah.
There's in here from Michelle Silverstein. Do you have any plans, ideas for how to identify flares with lower log E, say less than 30, so that there's more overlap with the TRAPPIST-1 results from K2? Do you understand the question?
So with flares with lower energies? Yeah. Well, actually, the light curves are really different. So there are ones where it's of high quality, so we could actually find smaller flares, but in most of the time they were just pretty noisy. So that's why we did the completeness correction for all light curves differently. So in some of the cases, it was quite easy to see these small flare events for the nearby and brighter stars. Okay. But in most of the time, it's really challenging.
Okay, thanks a lot. This concludes this session 3. Thanks to all the 4 speakers for this second part. And there are, of course, more discussion on the Slack. So specifically the presenters, if you go there and check if there are more questions related to your presentation, that would be great. The other thing is that we now have a long break, nearly 4 hours, and we start again at, depending on what time zone you are in, but if we take UT, it's 7:30 p.m., 1930. That will be the panel discussion on exoplanets, as you were already told. So please come back in 4 hours if it doesn't end in the middle of the night in your time zone. But thanks again to all speakers, and see you in 4 hours.